Hi guys, we will continue with specific heat capacity. Now gonna solve another problem. Remember the other day I told you that I had a problem when I was recording, and today I also had problems. But anyway, I'll try to do it at my best. Hot just means that copper coin is placed in 101 grams of water to cool. The water temperature changes by 8.39 Celsius, and the temperature of the coin changes by 68 degrees Celsius. What is the mass of the coin? Now we are talking about a situation in which a piece of metal, in this case a coin, is going to be placed into a container with water. Now, why? Because they want the copper coin to be cool. So it means that initially the coin was hot. Okay. And after they place it in this container with water, this coin becomes cooler. Now, what do we know about this? We have two objects, two substances, by the way. One is the copper coin. Remember, in these exercises we need to separate both substances because they have different givens. So we have the copper coin and we have water. This is my system. Okay. Now, what do I know about water? That I have a mass of 101 grams. The water temperature changes. The temperature of water is, the change in temperature of water is 8.39 degrees Celsius. Now, because the coin becomes cooler, that means that initially it was hot and then it was cool, and the water was cool and after it became hot. That means that the temperature of water, as it is increases, thus a change in temperature will be positive because it is increases. But in the case of the copper coin, because they want the temperature to be cooler, we are going to consider the change of temperature to be negative because it becomes cooler, so it loses temperature. As it loses, we know it should be negative. So we say that delta T of the coin, the temperature change in coin, is 68 degrees Celsius. As it gets cooler, the symbol must be negative. Now they are asking me the mass of the copper coin. Now, what else do I know that it's implicit, that is not given in the word problem? I know the specific heat capacities. As I know that the coin is made of copper, the specific heat capacity is Cp 3.87 times 10 to the second power joules over kilogram Celsius. Now, of my water, it's right here, is 4186 joules over kilogram Celsius. That means that this mass that I have in grams must be converted to kilograms. By how? You know to do conversion, just divide by 1,000. So this will be 0.101 kilogram. Now, what's next? Well, we have the main equation for specific heat capacity, that is Q absorbed equals negative Q released. Which one releases and which one absorbs? The one that absorbs is the one that gets hotter. In this case is water. And the one that releases is the one that gets cooler. In this case is coin, the copper coin. So we say, as we're more interested about mass, this mass, we can directly use the equation that I have right here. So you can use this one exactly, or we can isolate. I prefer to isolate because I can include all the givens in one single procedure. So Q of water will be mass specific heat capacity and delta T equals negative mass specific heat capacity of copper delta T. My water mass is 0.101 kilograms. Cp is 4186 joules over kilogram Celsius. And delta T, change of water, is positive 8.39 degrees Celsius. This is equal to what I have in the other side, that is negative the mass, that is my unknown, my Cp, my specific heat capacity of copper, that is 3.87 times 10 to the second power joules over kilogram Celsius, times my change in temperature of copper, that is negative 68 degrees Celsius. Again, this negative is because the copper coin gets cooler, so it loses temperature. As it loses temperature, the change in temperature is negative. So do the math here and take a look. My kilograms and kilograms will be cancelled, and also my Celsius and Celsius will be cancelled. So here my answer will be in joules. Now perform this in the calculator. Well, this gave me 3,547.17 joules. This is equal to what I have in the other side, that is negative my unknown, which is the mass, times this. I got negative 26,316. Here joules, Celsius and Celsius are going to be cancelled, so my answer here is joule over kilogram. Now negative and negative, it's going to make positive, so 3,547.17 joules divided by, remember, negative and negative is positive, so this will be 26,316 joules over kilogram. Or you can take it with you. Okay, I'm gonna take it better. This is equal to negative mass. So perform the division. I got I'm gonna continue here. Negative mass equals negative 0.13 kilogram. This is my answer. Okay, now take a look here. My joules and joules are going to be cancelled, and here negative and negative are going to be cancelled, and you can say that mass is 0.13 kilogram, and this is your final answer. This is my coin's mass. Okay, we have another sample problem here. It's a little bit more complex. It says a 0.05 kilogram metal bolt is heated to an unknown initial temperature. So basically here they are telling me that the initial temperature of the metal bolt is unknown. Then it is then dropped into a calorimeter containing water, specifically 0.15 kilogram, with an initial temperature of 21 degrees Celsius. The bolt and the water then reach a final temperature of 25 degrees Celsius. This is what I told you the other day. Two objects reach their thermal equilibrium, and in this case the thermal equilibrium that they both reach is 25 degrees Celsius. So this one will be the final temperature of both substances, the metal bolt and the water. If the metal has a specific heat capacity of 899 joules over kilogram Celsius, find the initial temperature of the metal bolt. In this case, we have two objects, the metal bolt and water. So as I told you, it's good that we separate the givens. Metal bolt and water. Now we need to identify which one gets hotter and which one gets colder. Usually water is the one that gets hotter, because you place heated objects in water in order to make them cooler. For example, if you are building if you are trying to, sorry about the noise, if you're trying to have to create a sword, for example, okay, you apply heat on it, and after, what you do is you place in water in order to make it cooler. So this is what happens here. The metal bolt is placed in water in order to get cooler. So metal bolt is gonna get cooler and the water is gonna get hotter. So water is the one that absorbs and metal bolt is the one that releases. Now in this case, we have our equation: Q absorbed equals negative Q released. And now we're going to point out the givens of each. Of water, I have a mass of 0.15 kilogram, and the metal bolt is has a mass of 0.05 kilogram. Now initial temperature here is unknown, and the initial temperature of water is 21 degrees Celsius. The final temperature for both is the same, that is the thermal equilibrium, and it is 25 degrees Celsius. Final temperature equals 25 degrees Celsius for both. And the metal has a specific heat capacity of 899 joules over kilogram Celsius, and water, of course, is 4186 joules over kilogram Celsius. So this is what you have, and we're gonna isolate for initial temperature. Now I suggest to work with the Holt equation first and then isolate for the unknown. In this case, the one that absorbs is water, and the one that releases is the metal bolt. So place the givens, perform calculations, and then isolate. This is what actually we're gonna do. So we have mCp delta T of water equals negative mCp and delta T of the metal. Mass of water 0.15 kilogram. I'm not going to write a Cp because of the space, but you know that is 4,000. And delta T is final minus initial, so you're gonna have 4 degrees Celsius. Remember, delta T, final minus initial temperature. 25 minus 21 is 4. Positive. Now here you have negative 0.05 kilogram. Cp of the metal, that is 899 joules over kilogram Celsius, and the delta T of the metal, that is, let's see, we don't know it. Okay, so it's delta T. We need to isolate for it. Okay, so you perform the math in both sides of the equation. Remember, Cp of water is known, and you cancel kilograms and Celsius with kilograms and Celsius, and you have joules. In the other side, you perform multiplication between 0.05 and 899. Gives you this negative, of course, because of the symbol of the equation. And then here's the moment where you isolate for delta T. You say delta T, or change in temperature of the metal. In this case, we're talking about the metal. I'm gonna write it here just for you not to forget. Delta T of the metal is, this one is remains in the other side with the same symbol, and 44.95 negative comes to divide, so it's gonna be divided by negative 44.95 joules over Celsius. Here joules and joules are going to be cancelled, and delta T is gonna be negative, and it gives me negative 55.88 degrees Celsius. So, does it make sense? I always tell you that we need to analyze our answers. Does it make sense? From the beginning, we said that the metal is supposedly getting cooler. It's not supposedly, that's the idea. They place it into the water in order to get it cooler. So, as it needs to get cooler, that means that it loses energy in the form of temperature. The temperature should be, the change of temperature should be negative, from hot to cold. And it makes sense. Take a look, our symbol is negative, so our answer makes perfectly sense. So guys, thank you for watching. I thought I was recording the other part, but actually I wasn't. I was talking alone again. Okay guys, this answer that I have here, that I told you, the change in temperature, it makes sense, right? We define it, we said it makes sense, but that is not the requested question. It says what is the initial temperature of the metal. So we're gonna take our definition of change in temperature, that is this one, final minus initial. So my final is 25 minus the initial temperature, that is unknown. You isolate for the initial temperature, so we're gonna be the final minus change in temperature. 25 minus change in temperature, which is negative. Negative makes a positive, so basically you add them. The initial temperature is 80.88 degrees Celsius. Now, does it make sense? Yes, totally makes sense, because that means that this metal bolt was 81 degrees Celsius initially, and after they place it in the water, it ends up with a temperature of 25 degrees Celsius. Sorry guys, I hate the noise, so I'll end up the video now. Bye.